Hello. In this topic, we are going to discuss about the reflection and transmission of signals or probably light rays by not a single layer but a stack of layers. Now, Lord Rayleigh in 1917, he raised the question that why some of the birds or insects exhibit the phenomenon of iridescence, that is multiple colors from their maybe feathers or wings. And likewise, even the case of a bubble or the bubbles of soap, they provided this rainbow-like uh, shine and rainbow-like reflection from their surfaces with multiple layers of various bubbles involved. Now, he explained this by studying the reflective properties of stack of thin reflective layers. And this is also observed in many other cases, such as geophysicists in their exploration seismology. They discuss about the properties of the reflective properties of the layers of the earth stacked one over the other. Now, Rayleigh, Lord Rayleigh, he solved this problem in the following way. First up, we will consider a few layers. Now, we will be considering a left stack of layers on the left side and few layers on the right hand side. There are multiple number of layers, there are not just four of them. So these are the left layers and these are the right layers stacked one after the other, and we are to consider, or we are to obtain the net reflection or the net reflecting coefficient, reflected light coefficient, and the net transmission coefficient when the reflection coefficient of the left layers is given by RL and its transmission coefficient is given by TL. The reflection coefficient of the right layers is given by R, subscripted with R, and its transmission coefficient is given by T, subscripted with R. So this is what we have at hand, and also there will be a few reflections and transmissions occurring in between, and we just name those coefficients for now as A and B, whose values will be determined later along with the values of R and T, that is the total reflection coefficient and the total transmission coefficient of all the stacks of layers put together. Now, whatever we'll assume that the rays or the signal that is being provided is from the left side of the screen, such that it is being reflected from the first layer of the stack. After taking all the combinations of the reflection into account, they are getting reflected eventually onto the left hand side because that's where the signal was approaching, and then finally some of it, after the transmission from various layers, some of them are some of the signal or part of the signal is getting transmitted with the net transmission coefficient obtained as T. We will be obtaining the expression for these reflection and transmission coefficient. So we will be giving a mathematical treatment to this otherwise complicated looking phenomenon. Now, although it does look complicated, but you will see how we can deal with it in a simpler manner by considering the single layer approach that we have been doing even in the case of the Taylor series that we considered. The sum of the series was obtained by the single case approach, and then we extended it to n number of cases. Here also we'll be doing a similar kind of an approach, and As far as the reflection and transmission coefficient is concerned, it will be obtained. Now, if there were two such layers, then one would have certainly thought that the transmission from one layer to the next layer and later on the total transmission would have been equal to the product of the transmission of the individual layers. Now that is pretty okay if we think about it in case of very less number of layers, but go on to think for a huge number of layers being stacked together, that would not be the result. The result would be something different that we will be obtaining over here. Now, to start with the solving of the problem, now since the transmission coefficient is TL for the left stack, it determines the ratio of the transmitted wave to the incident wave. So there was an incident wave out of which some amount of wave has been transmitted. So the greater the transmission coefficient, the greater the amount of wave that was transmitted. The less the coefficient of transmission, the less will be the amount of allowed waves transmitted with respect to the incident wave. So you have to put all of those things in the mind. And also the case of reflection, the coefficient simply means that the percentage or the amount of the reflected wave that was or the amount of the wave that was reflected out of what was incident on the surface. So that is how we determine those coefficients. The greater those coefficients, the greater are the chances of those phenomena occurring. The greater the coefficient of reflection, the greater will be the reflected wave in comparison to the incoming total amount of incident wave. Okay, now with all this, what would have been the case that we would have had, this is a would have case, would have been TL with all those left transmission occurring, TL times of TR would have been T. But that's not the case. As I said, we will be obtaining the result to be something different. Now we'll have to consider the figure. Now the unknown quantities to be determined are simply R, T, and before that it will be necessary for us to obtain the values of A and B as well. Now let us consider that a wave of incident wave of strength 1, we are taking a unit strength, that is incident on the left stack, the first surface of the left stack, and we have the right stack later on. Now we determine the coefficient A first. Now as far as the coefficient A is concerned, as you can see, A is going towards the right. Now what does A contain? If you go on to analyze the value of A, now with all those stacks considered on the left hand side, that unit strength of the incident wave that will be coming over or being incident on that left stack, out of that, with the transmission coefficient that is there for the left stack, that is TL, so TL amount of light will be transmitted. So 1 into TL will be the amount of light transmitted. But as you can see, there will be a B which will be reflected back from the second stack, that is from the right stack. And what is the reflection coefficient? What is the reflection coefficient or this contribution to the left going reflected wave? So that B, that will be hitting that left stack, it is any wave that has been reflected from that right stack, but that would be reflecting towards the left stack. Now the left stack has a reflection coefficient RL, and as a result of that reflection, it will be again coming back in the direction of A. So A not only has the transmission of that unit incident wave with multiplied to the transmission coefficient from the left stack, it will also have, A will also have the B factor, I name it as B factor for now, which on reflection from the left stack once again will be directed towards the A, and the reflection from the left stack would be giving a percentage RL out of it. So this is the amount of wave that will be contained in that A. Now what about the case of B? Now B, as far as we can see over here, A would have approached the right stack, and then it would have got reflected, and the reflection would have been contained in that B, isn't it? So B is nothing but A times of the reflection coefficient of the right stack. What about T? Now T is equal to, as you can see, the T has been transmitted out, the final total transmission that we are talking about. Now because there will be no reflection involved, or no reflection carried in that, so simply the transmission would carry all that was incident from A multiplied to the transmission coefficient of the right stack. So you need to be very careful about all those parameters that we have set over here. Finally, what about the reflection coefficient that we were looking for? Now the reflection coefficient here will be equal to, first up we'll have the reflection from the left stack, that is okay, that is fine, and then the B that would have approached the left stack, it would have got transmitted, the part of it would have got transmitted, and the part that would have got transmitted is simply B times of the transmission coefficient of the left stack. So we have all these parameters set for us as of now. Now first of all, we will see from these two, what about the values of A and B? Can we obtain the values of A and B? Well, if we put the value of B from that second equation over to the first equation, then what do we have? B is A times of RR. So R subscripted with R. So A is simply equal to TL plus, instead of B we are having A times of R subscripted with R, that is the reflection coefficient of the right stack, multiplied to the reflection coefficient of the left stack. Now this is the value, this is not exactly the value of A. The A will be obtained when we take this to be common, the A factor to be common, and we have 1 minus RR times of RL, and that leaves TL on the right hand side, and finally we get A to be equal to TL over 1 minus RR times of RL. That is the value of A. What about B? B is simply A times of RR. So we have B to be equal to A, that is TL over 1 minus RR times of RL multiplied to RR. This is the value of B. It's all there in the formula. Now with the values of A and B available to us, we can simply equate or obtain the value of the unknown quantities, that is T and R, and our aim, our objective is met. Now one thing that I would like to bring to your notice is that if we are observing the case of the right going wave A between the layers, and that does not simply contain the transmission coefficient of the left layer, that is TL. A here does not only contain TL, it has a factor 1 over 1 minus RL times of RR. And if you remember the Taylor series expansion of 1 over 1 minus x, it was simply x raised to the power n. This factor, I'm writing it over here, this factor 1 over 1 minus RR times of RL is simply going to be, if you take it for n number of times, n taken from 0 to infinity, then it was RR times of RL all raised to the power n, n extending from 0 to infinity. I'm squeezing it the figures over there, let me just elaborate that for you. This is summation of RL RR raised to the power n, n extending from 0 to infinity. This is what we had obtained in the Taylor series. This simply tells us that the quantity RL and RR, the product of that shows that this term accounts for the wave that bounces back and forth between the two stacks, that is the left and the right. We can actually consider any layer as the left and any layer as the right. So it's essentially the back and forth transmission or back and forth movement of the signal or the wave between any two given layers. Here we have considered the right and the left stacks, but it can just mean any two layers and the bouncing back and forth of the signal between those two layers. Right. Now, this simply also implies that we need to call this type of occurrence between the two layers as the reverberation term. So this term is simply called the reverberation term because of the signal reverberating between the two layers. And it plays an important role in obtaining the response from the layered media, even in seismography or in case of those in that iridescence that we observe. Now, with all done and dusted, we can simply calculate the value of R now. So R will be equal to RL plus B times of TL. B, remember, is this. So we have the value as RR times of TL multiplied with that TL over there with B, TL squared 1 minus RR RL or RLR, whatever. And then finally the value of T, that is the transmission coefficient, that will be equal to, as we can see, that is equal to A times of TR. So A being equal to TL over that. So we have TL times of TR over 1 minus RL RR. So in the beginning, I had already mentioned that this won't be the case for the transmission. It won't simply be the transmission of the left stack multiplied to the transmission of the right stack. As you can see, there's a reverberation term that is involved between with that transmission total transmission phenomenon. So with these formulas available to us, how exactly do we expect to do the calculation? Because here we have a left stack, here we have a right stack, and I said that that's not always the case. We may not have any left and right, but we will be having one layer after the other. There will be no gap for that A and B. But I also mentioned that with any two random layers considered, we can just assume one to be on the left and the other one to be on the right, and we will have those two layers to be treated, one as the left stack and the other as the right stack. So let's see exactly how this calculation can help us. Suppose we have uh, n as a single thin layer. Now n here simply means 1, 2, 3, so it goes on, and there will be a reflection coefficient associated with each layer. So 1 will have a reflection coefficient R1, R2 will be the reflection coefficient of the second layer, R3 will be the reflection coefficient of the third layer. Similarly, they will have transmission coefficients as well. So T1, T2 and T3, they will be the transmission coefficients of the respective layers. And let us say we have stacked n such layers. That means it's running from 1, 2, 3 right up to n layers. So we are having the nth layer, which is having Rn as the reflection coefficient and Tn as the transmission coefficient. Now the net reflection and transmission coefficient, let that be equal to Rn and Tn. This is the net or the total reflection and transmission coefficient of this stack of n layers. Now we supposedly wish to add one more layer, that is the n plus 1th layer is added to it, to this stack. Now that is now treated as the right stack, and it has probably the reflection coefficient now for that stack is simply that layer is Rn plus 1, and its transmission coefficient is simply Tn plus 1. Now with that available to us, so with all this information available, that is the total reflection and transmission coefficient of all those n layers, and finally we have one more layer added to it, and how would it really impact the reflection and transmission coefficient, the net reflection and transmission coefficient? So we can use this formula, and we will be using the values of Tr and Rr. So this replaces Rr, that is Rn plus 1, and Tn plus 1 replaces Tr, because that single layer is now treated as the right stack. Single layer but a right stack. So now we'll have the reflection coefficient of the n plus 1 number of layers, which will be given by this formula. That is, we have the left stack, that is Rn, we had it for the left stack, then plus this will be Tn squared, and then for Rr we'll use the value Rn plus 1. I hope you're getting the point right now. And all of that divided by 1 minus, this will be, first of all we'll be having that to be equal to Rn, that is the reflection coefficient of the left stack, and that will be multiplied to Rn plus 1, that is the reflection coefficient of the right stack, which is the single layer that we had, and as I said, that will be replaced. Now I leave it to you to determine the transmission coefficient of this total n plus 1 layers. I think it will be fairly easy with all the parameters and data given to you. Just like the case when you provide the data to a computer, it can calculate multiple number of times with the available data, and it will give you the correct result. But if you go on to imagine where exactly we would have started this, probably in a zero medium where there were no stacks initially. So if we start right from the very beginning where there are no stacks involved, then we first add one layer and then one above it, and then we start putting on those stacks. Now what about the case when there was no layer? Now at that point of time, obviously there would have been no reflection, because a layer has to be provided in order that the given signal bounces back. So in that case the transmission will be completely of the value 1, because that is how we have provided the strength there right at the top, that is the value 1 that was provided, that is the strength of the incident wave that has to be considered wholly. And then you add a very thin layer, start adding that, and then you have the reflection and the transmission coefficient associated with that layer, and then you gradually build up with one after the other. Now Lord Rayleigh, he prepared the foundation for a theory that later became known as invariant embedding, which turns out to be extremely useful for a number of scattering and diffusion problems. And the main conclusion of the treatment of this discussion is that the transmission of combination of two stacks of layers is not the product of the transmission coefficient of two separate stacks. However, paradoxically, Berry and Klein, they in their experiment related to transparent mirrors that consist of a large stack of layers of random transmission coefficients, they obtain that total transmission coefficient to be the product of the transmission coefficients of the individual layers, despite the fact that multiple reflections do play a crucial role in this process. That was a paradox, of course, but this is the result that we obtain. This is the value of the transmission and reflection coefficient. The transmission here is not dependent on the product, but it also has a reverberation term. So that's it from this video. We'll be discussing more such facts in upcoming videos. Till then, thank you for watching.